we continue our discussion, blue ink seems to show up better. Here we go. So this will be lecture 18 for us. We're going to continue our discussion of the second law of thermodynamics. Now again, we're in the Changle and Bowles text, so for us this is chapter 7. This will be page 1 of notes here. Right, and so we introduced last time the idea of the second law. We said that the second law tells us that a change in entropy is always going to be greater than or equal to what causes the entropy change. And one of the main ways we're going to change the entropy is to heat a substance up. So a change in entropy, a differential tiny little slice of change in entropy, is going to equal or be greater than the amount of heat transfer that causes the entropy change divided by the temperature at which the heat transfer occurs. Heat in, if I add heat to a substance, that increases the entropy. So heat in is positive, causing a positive entropy increase. Again, entropy being chaos or disorder or unpredictableness, if you will, of the molecules. Now, this inequality, this differential inequality is the purest, rawest form of the second law. In a more practical, useful form, if we integrate this process, or if we integrate this equation, or inequality, if you will, for a process from state 1 to 2, it looks like this. So I integrate both sides of this expression. That's going to give me delta S. And rather than writing it as an inequality, we're going to say that it's equal to, and again, I'm going to write this as the integral of dq over t. That's add up all the heat transfer divided by the temperature at which it occurs, and add to that the amount of entropy generated. And what this is saying is, again, the entropy change is greater than the quantity or the heat that causes the entropy change. So this is the amount that it's greater by. This is the entropy generated. And basically the second law is saying entropy is always being generated. To the best of our knowledge, we cannot destroy entropy once it exists in the universe. Now, if you divide all terms by mass, then you get little s. So that's little s2 is equal to little s1, and that's equal to the, or I'm sorry, little s2 minus little s1 is equal to the integral of d little q over t, heat per unit mass, plus little s gen. Now, so just fair warning, as you can see, my s's, whether they're upper or lowercase, look very similar. I try to draw my lowercase s's excessively small. And unfortunately, just fair warning, my s's do look like an integral sign. I try to draw the integral very large, especially because this is the integral of this fraction quantity here. Okay, but this is per unit mass. All these are per unit mass. If you multiply, as we've seen with control volumes, sometimes I need to measure something per unit time. So if I multiply by m dot, if I multiply each of these terms, well, not these terms, but each of these terms by m dot, then you've got m dot times little s2 minus little s1 is equal to the integral of del big q dot over t plus, let's say, big S gen dot. Now again, the dot above a variable means it's being measured per unit time. Lowercase means it's per unit mass. Which of these do you use? Well, Steve, which one's right? Well, they're all correct. They're all the same equation. I've just manipulated them a little bit. Which one do you use? I don't know. Depends on your situation. Every situation is different. Do you have the mass? Do you know the amount of mass? If you don't know the amount of mass, perhaps we work the problem per unit mass. And then it doesn't matter how big or small the system is, we can figure out for every unit of mass what the entropy change or the entropy generated should be. Maybe it's, again, if I'm working with control volume, it probably doesn't necessarily make a lot of sense to worry about the total amount. Maybe it makes more sense to worry about the rate, the amount per unit time. So again, which of these do we use? Well, they're all correct. You could use any of them. It depends on what you have and what makes the most sense for your problem, and I can't tell you that without seeing your problem. Again, we're training engineers and trying to train you guys to where you don't have to memorize everything and plug and chug. We're training you to learn how to figure things out as you go. Again, the problems you'll be solving may not exist yet, so I can't teach you how to solve problems that don't exist yet. I just try to teach you how to solve any problem. So, what else do I want to say here? And again, remember the rule. The entropy generated is always positive or at least 0. If you get a quantity, right, this is the rules. It's basically one rule. Entropy generated is always positive. If you solve for an entropy generator, you calculate or estimate an entropy generated and you get a negative quantity. First and foremost, double check all your signs, double check all your calculations, check all your units. A lot of you guys are ignoring your units. That's going to get you in trouble later. Double check everything, and then if you still have negative entropy generated, that's just an impossible process. We can't actually have entropy being destroyed to the best of our knowledge. Okay, so did that. That's review events. So that's a whole page of review there. 2 ways we can increase or change. I would like to say 2 ways we can change. I don't know if increase is the best word. I might suggest 2 ways we can change the entropy of a system. Okay? There are 2 ways we can change the entropy of a system. One is entropy exchange via heat transfer. Right? So we can heat something up or we can cool it down. That will change the entropy of a system. And we can also have irreversibilities. We talked about this in Chapter 6. Those are things that cause the process to be irreversible. Right? And what these amount to is the entropy change via heat transfer. That is this integral of dq over t. And the irreversibilities are the entropy generated. Right? And the reason I say change and not increase is because heat, we could lose heat. Right? You could cool the system down, and that's going to decrease the entropy of the system. So increase is not necessarily correct. There are 2 ways you can change the entropy of a system. You can only increase the entropy by generating it, because we can't destroy it, but you can cool something down and decrease the entropy of the system. Okay? All right, so 2 ways I can change, and you can see that mathematically, right? Based on the second law, the entropy change is a function of 2 quantities, heat transfer per temperature and what's being generated. Okay, so there's 2 ways we can change the entropy of a system. We can see that mathematically. If you have an isentropic process, iso, or isen in this case, referring to constant, entropic meaning entropy. If I have a process that is isentropic, that means constant entropy. Then the entropy of the system does not change from start to finish. That there are 2 things required so we can assume it's isentropic. If they tell us that it's reversible, okay, reversible could be things like they tell you it's no friction. In your text, a lot of times they'll tell you, somehow they'll tell you it's the best case scenario. And what that means is they might tell you max output, right? Or minimum input. I'm going to write this in the notes because it's hard to write with your finger. And I even misspelled input. Right? A reversible process. A reversible process tells us that the entropy generated is 0. How do we know that? Well, it's if I have a best case scenario, then I know my entropy is being generated as 0. Now, the ways that this text will tell you is they'll tell you maybe you've got max output, or maybe you've got minimum input. Those are the main ways that they're going to tell you. What I like to tell you is do this. Think about the purpose of the device. Okay? Think about the purpose of the device. And once you think about the purpose of the device, is this the best version? For example, a turbine, if you will. The goal of a turbine is to extract power or work from fluid flowing through the system. The best case of that is, the best version of that would be the turbine that generates the maximum work output or maximum power output. A compressor is a device that puts work into the system or into the fluid stream. So the reversible compressor would be the one that requires the least amount of work input, the minimum work input. A nozzle is a device that increases the kinetic energy of a fluid. So the reversible nozzle would be the one that has not the max output, but the maximum exit velocity. What is the purpose of the device? A nozzle increases the kinetic energy of the fluid, at least that's typically its purpose. The reversible nozzle is going to do that the best possible way, and it's going to produce the maximum exit velocity, or the highest kinetic energy change. Again, what is the purpose of the device? Is this the best version of that device? If they've told you that in the problem statement, and you have to think about this, okay? If they told you that in the problem statement, have they given you enough information that you can assume that it's reversible? Okay. If they have, then you can assume that the entropy generated is 0. And when you look back at the second law, what happens? Then, will this go? If this guy goes to 0, then that's one less term I've got to worry about. Kind of like with the first law. Can you assume there's no heat transfer? If you can, then the first law gets easier to deal with. Same thing here. Have they told you enough information to assume the entropy generated is 0? If they have, that's one less term to worry about. Let's worry about then the other terms. Okay, this is lecture 18, page 2. Now, so let's look at the other terms. So if, let's say I've got some way to deal with this guy, and then we look at this guy. What do I do with this guy? Well, I think that's my next slide. Let's say that. Oh yeah. Could be, make sure I'm still on the screen here. Yeah, just barely. It could be adiabatic or well insulated, right? Heat transfer entropy change, right? Now our text likes this partial integral, and it's kind of scary because you've not had partial integrals and probably never encountered one before, and that's okay. We're not going to do any partial integrals. Don't worry. We're not even going to do, in this class, I'm not even going to give you any integration by parts. Simple integrals, yes, I expect you to do those, but anything more complicated than simple stuff, it's a little beyond what we're going to ask you to do. So no partial integrals here. We just have to understand, what is this thing telling us? It's telling us take everywhere heat transfer occurs and add it up and divide by the temperature. Okay? Now, if it's adiabatic, then if I add up a whole bunch of zeros, I get 0. Okay? There's another scenario where we could have heat transfer occurring at a constant temperature, and those are the two main scenarios we're going to deal with in this class. Okay? That's a nice stopping place. We'll pick up the next video there.